Since we didn't have access to timing gates, we would have to put cones in 5 meter intervals and have someone time the other person. But obviously this then includes perspective error and human error. I mean that our results wouldn't be as reliable as using timing gates. But that is the best we could do. Looking at cameras now to record and then analyze later on. Ideally, you'd want to use 3D cameras. So this would be cameras scattered around a room, looking at little sensors on a body, and then that would be able to generate a 3D model or an image on a computer. Then be able to accurately show what the performer is doing at each set time. And an example of this would be something like Vicon, which is a software used to do this. We have used cameras to record both tests, so both the 20-meter sprint test and both the vertical jump test, to then be able to look back afterwards and fully analyze. So you'd also want to use a high-speed camera, where a high-speed camera is able to take thousands of pictures per second, which then allows for a super slow-mo later on for proper analysis, so that you can look at a set and a specific time. For example, in the vertical jump, the specific moment when they jumped up and stops touching the force plate, for example. You'd also want a faster shutter speed in your camera to create a clearer image. However, this also creates a darker image as well, as there's a faster shutter speed, meaning less light isn't allowed into the camera, causing that darker image. So you'd either want a well-lit room, and would have to test this before the experiment, or you'd want a slightly slower shutter speed, so you still have a clear image, but then you also have that bright room. It just wouldn't be as clear. You'd also need to take into account frame of view when setting up your camera. So, for example, in the vertical jump test, if the performer is doing a vertical jump and you'd need to be able to allow space above them in the camera frame for when they will jump, because you don't want to then not be able to see them for half the jump or the experiment investigation, as this would then be not very reliable or would be hard to analyze later on when you look back on your footage. You also want to remove perspective error by having the camera set up perpendicular to the plane of motion that the performer is moving on. So in the 20-meter sprint test, since they're running in a straight line, a set plane of motion, you want to be perpendicular to that line of motion of those timing gates, so then you get correct angles and stuff like that. Similarly to the vertical jump, if you're perpendicular, then you can then later on accurately tell like what angle their knees were bent at as they jumped. Whereas if you weren't perpendicular, the angles would be slightly off. I mean that you then incorrectly analyze your data later on, causing inaccurate data. And then this also could cause wrong times through your timing gates if you're not using your timing gates, for example. And then also, before you record your footage, setting up your camera, you need to check for tilt. So you need to make sure your camera is balanced before recording, to then also prevent any perspective error or angles being recorded wrong. These are the results that were gathered from the investigation, looking at my performer. So this is my performer here, obviously just under the group average, nowhere near the NBA elite results of close to 100 centimeters in height, and obviously this is my better performer. So it's clear that my performer would need to work on their power and height and their vertical jump, as this could potentially be letting them down during a basketball game. And then similarly, their peak power during the vertical jump. Obviously, my performer of approximately 3,500 watts, obviously nowhere near the better performer of approximately 5,500 watts, and then obviously the NBA elite athletes approximately 8,200 watts of power, something like that. And obviously my performer then potentially need to work on this, but this would all be further analysed in 6.4 assignment. Similarly, the linear motion. So this is the results of my performer here, of my chosen performer, and you can see the distance and time. A distance time graph here is a slight curve, so you can show that they're accelerating here throughout, which shown here, acceleration time graph. In this first second, they accelerate quickly to 5 meters per second squared, and then obviously in this next second, they're not actually accelerating because they're traveling at a constant speed. And then these last few seconds of running, they're accelerating once again, so again even quicker, and their velocity is increasing. And this is shown here, where their velocity increases up here to about approximately 5 meters per second, and then actually it shows that they decrease in velocity, so they decelerate slightly to just under 5 meters per second. By the looks of it. And then obviously these last couple of seconds here, they accelerate once again to finish with a velocity of approximately 6.5 meters per second, and finish in a time of about approximately 3.7 seconds. So you can tell that they're constantly or not constantly speeding up, but the overall speed does increase throughout, apart from this second here. And then obviously my performer here is slightly slower than the group average of about 3.7 seconds. And yeah, they're slightly slower as they have greater time. And then obviously the NBA elite athlete of about 2.4 seconds in a 20-meter sprint, and then my better player, another better player in this group of results, got about 3.4 seconds approximately. So this could also be something my performer would need to work on. But obviously this would then be further analysed and developed in 6.4. So to finish off, evaluating the numerical model, there are advantages and disadvantages to this model. With some advantages being it's good for minor changes to elite performers. So as they become elite performers and get better and better, it's likely that their technique and performance is obviously of the highest level, but it only needs micro changes and minor changes, slight changes to their technique or their performance, to then be able to further improve. And this is a good way to do it. So using the numerical model, as for example the camera shots using super slow-mo, or the Vicon 3D imaging, to be able to properly assess where they are lacking in their performance or technique, for example. Another advantage, advanced analysis, means that they can precise changes to performance. So this advanced analysis shows that they can then specifically identify where exactly, probably to the millisecond, that they are lacking, and that is then able to be tweaked and changed, so that goes in with this minor changes to their elite performers. And then also these results can be compared to normative data, and the normative data then creates motivation for the performers, as they then have goals to and times to strive to get to and try to aim to get to them. But then also makes it easier for coaches for a selection of their teams, as then using a wide range of tests, they can then see who fitness-wise is best overall, but not necessarily skill-wise. Some disadvantages of this: there's limited access to these advanced equipment, and it's difficult to use. So it would only really be available in universities or high sporting facilities. So it would only be available to those elite athletes, not those low-level, just county, casual, amateur leagues, as they wouldn't have the finance or the facilities to do this. And it also, as it's difficult to use, you'd need correct training or someone that knows exactly how to correctly set up all these tests and facilities, and then able to correctly and specifically analyze all this advanced technology and results they have received. It also requires a complex understanding of physics of the correct analysis. So using this numerical model, there's a lot of mathematics and physics that goes into it. For example, the Newton's laws of motion, for example, that's very physics based. And obviously this gets into much more detail and much more depth as you look more into it. And so a professional biomechanist is then needs to be able to correctly understand all of this and know exactly what these results they've gathered to correctly mean, so then they correctly analyze it and then give it back to their elite performers. Also, this isn't specific for performance overall. So elite performer could have really good results in all these tests. They could have amazing speed in their 20-meter sprint test or amazing power in their vertical jump test. But if they don't have the skills to work with their abilities, then their overall performance isn't going to be amazing. So they could have it could be good for that area of understanding their performance, but bad as it doesn't take into account any skills in a game situation. And finally, there requires a complex setup for reliable results. So that, for example, the camera setting up, that must take hours to precisely set up the camera. For example, the camera angle, the shutter speed, all that stuff, to be able to prevent perspective error and correctly have useful data after, to then be able to correctly analyze it later on. And that would take potentially hours to set up correctly, to have exactly precise data, and would take up a lot of time and is very, very time consuming.